Assalamualaikum and hi everyone, we are from Avengers. So today we will present to you guys about our project, which is sustainable synthesis of oxygen and water via ozone and hydrogen peroxide reaction. Here is our content that we are going to present today. Our objective is to design a sustainable process for the synthesis of oxygen and water using the ozone and hydrogen peroxide, which is our main reaction is the ozone that will react with the hydrogen peroxide will produce the water and also the oxygen. We have ozone and hydrogen peroxide that will act as our reactant, and our primary product are oxygen and water that are widely used in medical application, industrial and environmental application. This product ensure that the process is both sustainable and environmentally friendly.
For the decomposition of ozone, there are two major pathways that can be used to decompose ozone, which are shown in equation 1 and equation 2. Since the K values of the reaction pathways are different, an overall Kc value can be found by taking the ln function of the concentrations. For ease of calculations, the general equation is used for applying parameters of ozone decomposition from the Kc values obtained from Kwon et al.'s research paper, with a molar concentration of 20 times hydrogen peroxide to ozone.
First, we will generate ozone by using the electric barrier discharge reactor to ensure sufficient ozone concentration to meet the stoichiometry requirement. Then, hydrogen peroxide is stored in a tank and fed into the process via dosing pump. It's to maintain the hydrogen peroxide concentration within the range to avoid the decomposition. After that, the mixed stream enter a CHCR where the reaction occurs under controlled condition to produce oxygen and water, where in the CHCR we have the agitator to maintain the uniform mixing of reactant, and we also have cooling system to prevent thermal decomposition of hydrogen peroxide due to reaction exothermicity. Then it will go to the separation unit to separate oxygen gas and liquid product, which is water. In this separation unit, we use gas liquid separator to remove oxygen gas from the water and unreacted hydrogen peroxide. After that, oxygen gas is collected for reuse or the other application. Then the liquid will send to the further treatment. Then, residual water is treated and polished to meet environmental discharge standard or for recycling purpose. This one is carefully designed to optimize efficiency, ensure the safety and minimize the waste. Therefore, for the reaction step, we have selected a continuous still tank reactor CSTR because of the reaction characteristic, where the reaction involves a gas-liquid system that requires efficient mixing for ozone dissolution in the liquid phase. A CSTR provides throughout mixing, ensuring the reaction progresses uniformly. The second one is the temperature control, where the reaction can be exothermic, making temperature control crucial to avoid thermal decomposition of the reactant. A CSTR with a cooling jacket or internal cooling coil ensure isothermal operation. And the third one is the scalability, where CSTR are easily scalable, making them suitable for both pilot scale and industrial scale applications.
The first impact on SDG is SDG 7, which is affordable and clean energy. This process will produce oxygen, which can be a valuable resources for industries which require clean and reliable oxygen supplies. This design can be integrated with renewable energy sources, thus reducing the reliance on fossil fuels. By converting waste products like ozone into oxygen, the process supports the broader transition to a cleaner energy solutions, helping industries to reduce their carbon footprints. Secondly, SDG 9, industry innovation and infrastructure. This process can be implemented in modular and scalable units, making it adaptable to various industries, from small-scale facilities to large-scale industrial operations. The innovation is central to the design, particularly in using waste, which is ozone and byproducts oxygen, to create valuable products. The reactor design must incorporate advanced control system, ensuring precise operation and optimization of reaction conditions, which leads to sustainable production. Thirdly, the SDG 12, responsible consumption and production. This process involves turning waste ozone into a valuable product, which is oxygen, contributing to a circular economy. This aligns with SDG 12 by reducing waste and ensuring efficient use of resources. The efficient use of hydrogen peroxide should aim for a high conversion, recycling and unreacted material to minimizing the chemical waste. The water produced in the process is either reused or treated, thus reducing the demand for freshwater resources and preventing unnecessary discharge of contaminants into the environment. And lastly is SDG 13, which is climate action. The production of oxygen, which is a key of element in mitigating the effects of climate change, contributes to climate action by improving air quality and supporting ecosystem. By converting ozone, which is a greenhouse gases, into oxygen, the process helps to reduce the overall atmospheric ozone levels, thus contributing to the restoration of the ozone layer. The energy efficient design reduces the carbon footprint of the process. By integrating renewable energy sources, the process can minimize its reliance on fossil fuels, thus supporting the global transition to a low carbon economy.
For the MATLAB simulation, the parameters used were K equals to 0.0807 liter per mole second, a V of 2.294 liters, and O3 initial concentration between 2 and 0.2 milligrams per liter, and the H2O2 concentration of 20 times the concentration of ozone. The flow rate was measured between 0.1 and 1 liters per hour. The operating conditions were at 288 kelvins at 1 atmospheric pressure. The reaction model used with the reaction rate stated in the slides, and the conversion and outlet concentrations are derived based on the reaction rate. The oxygen production was also derived based on the stoichiometric relationship. For the assumptions, V was assumed to be equal to V naught since the reaction is a liquid reaction. All the reactions are also irreversible and follows an elementary rate law. The reactor has a negligible pressure drop at isothermal conditions and operates at steady state. There are also no spatial variations inside the CSCR. The manipulated variables were the feed flow rate and initial concentration of ozone to change the conversion. These are the MATLAB scripts, and these are the output of the MATLAB simulations, where we can see the conversion versus flow rate and initial ozone concentration, along with oxygen production from the same parameters.
Okay, I'm in charge of the manual calculation and data analysis using Excel, and here's the Excel table for our output data, the data we use to plot the MATLAB graph. So let me brief you quickly on how I generated these tables. Basically, I just export the results to Excel by tabulating these two variables, which are the initial concentration of our main reactant, ozone O3, and flow rates within the range from 0.1 to 1 liter per hour, originating from the assumptions we have made. So these two values will lead us to the final conversion of the products and also the value of the actual moles of oxygen produced. From here, we know that the initial concentration equals to 0.42 and flow rate is equals to 0.1 liter per hour. We will get the highest conversion using these two values. In order to get this x equals to 0.8484, first of all, by simple formula derivation, we'll get this formula for conversion. Then we'll also learn about this formula. Space time tau equals to volume over entrance volumetric flow rate, where volume is 2.294 liter and flow rate is 0.1 liter per hour. Then we'll get tau equals to 82584 second. This is how we get the final concentration of O3 by substituting the values inside the formula. X equals to 1 minus initial concentration over final concentration, we'll get x equals to 0.8484. Now we need to calculate the product yield. The yield is equals to actual mole over theoretical mole of O2, and from the chemical equation we know that 1 mole of O3 equals to 2 mole of O2. Thus, by multiplying initial concentration of O3 by 2, we'll get the theoretical mole of O2 generated. While for the actual value, we need to times initial concentration by the conversion 0.8484, and then times the stoichiometric coefficient 2 again to get the final value. Finally, the yield we obtain is equals to 84.84%.
Water will flow from the water tank to the ozone generator, where at the ozone generator, it will inject with the ozone and the hydrogen peroxide. The process will occur at the reactor, where water, hydrogen peroxide, and ozone will produce oxygen, and excess of water and hydrogen peroxide and ozone. And to reduce the temperature, it will go to the heat exchanger before go to the spiration unit. At the spiration unit, oxygen will release at the top, and water, hydrogen peroxide, and ozone will go to the treatment unit. And at the treatment unit, will release water, H2O. Here is the AutoCAD simulation for our process. From the simulation, we get the water tank, ozone generator, reactor, heat exchanger, spiration column, and treatment unit. From the AutoCAD simulation, we also know how the process occur from the one component to the other component.